Alright, here what we're going to do is look at momentum versus energy. What are the impacts and ramifications? What do they say differently about situations? We're going to start with an elephant. So here's our elephant. It's rumbling along at 2 meters per second, and it has a mass of 10,000 kilograms. And here you are, preparing to stop the elephant. And you're going to apply a force of negative 200 newtons. Why negative? Because you're going to apply the force, of course, this way. Now what we're going to do is we're going to look at the momentum of the elephant, the change in momentum, the time over which that will take place, and we'll also look at the energy involved and the distance over which that takes place. So we'll start off with momentum. The momentum of the elephant is pretty simple to calculate. We just do the mass of the elephant times v, which in this case will be 20,000 newtons times seconds, or 20,000 kilograms meters per second. Okay, so that's a lot of momentum. What we'll do now is we'll figure out, well, how long will it take for you to stop it if applying 200 newtons of force? So our change in momentum needs to be the final minus the initial, so 0 minus 20k, which means that we have a net decrease of momentum of 200 kilograms meters per second. And if we can apply a force of negative 200 newtons, that leads to, so the force times the time equals the change in the momentum. We can rearrange this so that we're solving for time. So the time that's involved would be the change in momentum divided by the force, or I believe that's just going to be 100 seconds. So it will take a total of 100 seconds for you to stop an elephant with 20,000 kilograms meters per second of momentum. This would really be equivalent to, 20,000 1 kilogram masses moving towards you at 1 meter per second. Okay, that's what the elephant is doing essentially, except it's 10,000 with 2 meters per second. Now, as far as the energy goes, we can calculate the energy pretty easily as well. So our kinetic energy, initially at least, will be 1/2 mv squared. V is only 2, so we end up with 1/2 of 10,000 times 4. And so what this gives us is, in this case, is working out in a rather strange fashion. I have 10,000 times 4. That gives us 20,000 joules. So it just so happens that in this case, the elephant has the exact same amount of momentum as it has energy. These are, however, two very different quantities. For instance, momentum is a vector, energy is not. You either have energy or you don't, whereas momentum can be going one way or another way. But what this allows us to do, though, as well, is we can use work equals force times distance. And we can use this to help us determine what distance is going to be involved. Hopefully we remember that work is equal to the change in the kinetic energy. So we're going to have a change of negative 20,000 joules with a force of negative 200 newtons. And I can already tell you right away, because it ends up being a very similar problem. If we have negative 20,000 divided by 200, we're going to get 100 meters. So this elephant is going to take 100 seconds in order to stop, and is going to slide us backwards over a distance of 100 meters in the process. So this is a pretty big deal in both cases. What we're going to do next is go forward and look at what would happen with a bullet instead. Okay, so we had just looked at the elephant, and the elephant's mass was 10,000 kilograms. The velocity was 2 meters per second, and that gave us a momentum of 20,000 kilograms meters per second, and a time to stop of 100 seconds when a 200 Newton force was applied to it. The elephant also ended up having 20,000 joules of kinetic energy and moved over a distance of 100 meters before it actually came to a stop. What we're going to look at now is, here's a bullet and here you are trying to stop it. This bullet, I've made the numbers so that it actually corresponds already to the kinetic energy that the elephant had. So I'm going to start there. And we'll start off with kinetic energy equals 1/2 mv squared. And if we plug in these numbers, 14.2 meters per second, and a mass of 0.01 kilograms, we end up getting essentially the same amount of energy. So this bullet has just the same amount of energy as the elephant did, in spite of being many, many times smaller. So we have the work that would need to be done. Work was equal to the change in kinetic energy, and it's also equal to the force times the distance. So because everything's the same, the work is the same, it needs to be negative 20,000 joules, and the force is the same. There's no difference in the distance that the bullet will travel before we're able to stop it. It's going to go 100 meters before we can stop it. Now the difference is going to be in the momentum in this case, because I kept the energy constant. Okay, so we're going to have a situation now where the energy was the same, but the momentum will be very, very different. So the momentum of this bullet is going to be the mass times the velocity. And this is essentially just dividing it by 100. So I'm going to wind up with, if I take 1,000 and divide by 100, I just get 10. Well, this is 14, so I'm going to get 14.142 kilograms meters per second as the momentum. Now, if you compare this to the momentum of the elephant, it's absolutely absurd that they end up having the same amount of energy, but that's the way that it works out. There's not that much object and there's not that much motion in the case of a bullet. Whereas with the elephant, you have a lot, literally 10 tons of object to try to move, and it's moving at a decent clip. You might say, well, this one's moving really, really fast. True. But the mass is so extraordinarily small in comparison. If you look at energy terms, what this means is this tells us how destructive they possibly are to us, right? So the elephant is very destructive, obviously. Something moving towards you at 2 meters per second with 10,000 kilograms. Very dangerous. But a bullet moving at 1,414 meters per second, also extraordinarily dangerous. So they have the same sort of destructiveness impact. However, when we look at the time frame over which this is going to occur, and I think this will be obvious once we do it, the time frame over which it occurs is going to be much, much less for the bullet than for the elephant. So the change in momentum is equal to the sum of forces times the change in time. We can get the change in time by just taking this change in momentum divided by the sum of the forces. So we just take 14.142 divided by 200. And this is actually a negative and a negative. And that gives us a time frame of 0.07 seconds. Compare that to 100 seconds. And the reason for this should be obvious, this difference that occurs. The bullet is moving really, really fast. So it's going to cover that 100 meters in a very short amount of time because it's moving so fast. Whereas the elephant, moving at 2 meters per second over a distance of 100 meters, is going to take 100 seconds. Now you might say, well, 2 meters per second over 100 meters shouldn't take 100 seconds. But bear in mind that the elephant is coming to a stop. So the average speed of the elephant is 1 meter per second over 100 meters, which means 100 seconds. For the bullet, it's going to average about 700 meters per second. So 700 meters per second for a distance of 100 meters is going to be 7/100ths of a second. This is where really the momentum has a difference. It has an impact. If you're interested in causing this to occur over a longer distance, that means that a much smaller force will be needed. I'm sorry, not a longer distance, over a longer period of time. A much smaller force would be needed. But that would then, as a result, increase the distance. So if you wanted to increase the time, you're also going to have to increase the distance over which this collision occurs. This is really a telling quantity, though, as well. Typically speaking, if you're trying to stop a bullet, it's not going to be very effective. You're not even going to be able to apply enough force to it, really, to cause you to move backwards at all. This is a really high-speed bullet, and it's actually not a very small bullet either. 10 grams is a sizable bullet, particularly to move at this type of a speed. But this is really the difference between the two. Other than the vector aspect of it, which takes into account direction for the momentum but not for the energy, we also have to look at and see what is really moving. How much motion is there? And in this case, there's really not that much motion. It's not that big of a deal to stop a bullet. It's not going to take you very long. Except when you look at the energy aspect of it. How destructive is it actually? And in terms of destructiveness, the bullet in this case is just as destructive as an elephant. But momentum-wise, there's a lot less going on. There's a lot less motion. So in terms of the time needed, or the force needed for that period of time, it's not that great. If you were willing to, say, extend this to 1 second, let's say that we didn't set the force, and we said, well, let's take 1 second. Let's do this for 1 second. Well, in terms of forces, the force that would be necessary to stop this in 1 second would be 14.14 newtons. That's not very much. So it's very easy to stop a bullet if you're able to give yourself enough time in order to stop it. It's not that hard. The difficulty, of course, would be that this distance would shoot up to 14.2 meters, or basically a kilometer and a half or a mile we'd be looking at. So, great. You wouldn't have to apply much force to stop a bullet in 1 second. You just need a mile over which to do it. For the elephant, it would be a somewhat different story. You want to take a second to stop the elephant? All right, you can do that. The difference, though, is if you take 1 second to stop the elephant, so if I say t equals 1 second here to stop the elephant, that's great, except that in order to do that, you're going to need, this will actually drop as well by quite a bit if you're only taking 1 second to stop the elephant, but the force needed will shoot up exponentially. Well, not exponentially, but it will scale up by 100 times. So instead of needing 200 newtons of force to stop the elephant in 100 seconds, you would need 20,000 newtons of force to stop the elephant in 1 second. So those are really mathematically the differences between momentum and energy.